welcome to this explainer. Today, we're doing something simple. We're looking up, way, way up. Now, when you look at the sky, you might just see empty space, maybe a few clouds passing by. But what you're actually looking at is a massive, invisible, highly interactive cause and effect machine. The Earth's atmosphere is this incredibly dynamic engine that dictates absolutely everything about how we live on this planet. So let's dive right in and see exactly how this machine works.
Here's a quick roadmap for this explainer. First, we'll look at our atmospheric container. Then we'll move on to the engine of weather. After that, we'll cover pollution and trapped air, look at the changing climate, and finally wrap things up with extreme weather events.
All right, Section 1, our atmospheric container. To really understand our air, think about the sheer scale of its timeline for a second. We're going way back to 4.6 billion years ago. Earth was violent, extremely hot, and volcanoes were just constantly erupting, spewing out water vapor, carbon dioxide, and nitrogen. But there was absolutely zero free oxygen. None. If you hopped in a time machine back then, there is no way you could even take a single breath. The real game changer arrived 2.5 billion years ago, when these tiny organisms called cyanobacteria basically figured out photosynthesis. They took in sunlight and carbon dioxide and started releasing oxygen as a waste product. Over millions of years, that oxygen built up, which eventually allowed complex animals to evolve. And crucially, it formed the ozone layer, which acts as our planet's ultimate protective sunblock against harmful UV rays. Fast forward to today, what exactly are we breathing right now? Well, if you grabbed 100 molecules of air, 78 of them would be nitrogen. That basically just fills the space. 21 of them would be oxygen. That leaves just one single molecule for literally everything else, including argon, water vapor, and carbon dioxide. Now, here is the absolutely crucial takeaway. Carbon dioxide makes up only about 0.04% of our air. It's a tiny, tiny fraction. But it is absolutely critical for trapping heat. Without that tiny fraction, we wouldn't have a warm, habitable planet at all. So, how is all this gas structured? Picture the atmosphere like a giant 5-story building. On the ground floor, from 0 to 12 kilometers up, you've got the troposphere. This is where we live, and it holds about 80% of all the air. All of our weather happens right here. Head up to the second floor, the stratosphere, and you'll find the ozone layer. It's super dry and calm here, which is exactly why airplanes fly at this altitude, to avoid turbulence. The third floor is the mesosphere. It plunges to a freezing minus 90 degrees Celsius, and this is actually where shooting stars, meteors, burn up. Then we hit the thermosphere, which gets incredibly hot and is home to the stunning northern lights. And finally, the exosphere, the penthouse, which just sort of slowly fades away into outer space. Moving right along to Section 2, the engine of weather. Everything with our weather starts with the sun in what meteorologists call the heat budget. First, the sun beams down visible shortwave radiation. The Earth then absorbs this energy and warms up, and then it sends that heat back out towards space as long-wave infrared radiation. But here's where the magic happens. Greenhouse gases in our atmosphere intercept and trap some of that escaping heat. This process brilliantly illustrates why our planet is actually livable. That trapped heat keeps the Earth at a very comfortable average of 15 degrees Celsius. Without this, our whole planet would be a frozen, uninhabitable minus 18 degrees. Now, as that heat moves around the globe, it creates different air conditions. You can kind of think of air as having two distinct personalities, stable and unstable. Stable air is, well, it's lazy. It really resists rising and just prefers to sit near the ground. This gives us calm, clear weather, but if you happen to live in a city, that lazy air traps all the smog and pollution right down where you're breathing. Unstable air, on the other hand, is highly active. Because warm air is lighter than the cold air above it, it rises rapidly. This vertical movement creates clouds and dramatic thunderstorms, but it also does a fantastic job of perfectly dispersing and blowing away pollution. Let's look at just a few more basic mechanics. You know what wind is? It's simply air rushing to fill an empty space, moving from an area of high pressure to an area of low pressure. But because the Earth is spinning, that wind actually curves. It's a phenomenon known as the Coriolis effect, which deflects winds to the right in the northern hemisphere and to the left in the southern hemisphere. And what about moisture? Think of warm air like a large sponge. It can hold a whole lot of water vapor. When relative humidity hits 100%, the air is totally saturated. That water vapor is literally forced to condense onto tiny dust or salt particles in the air. And boom, you've got a cloud. Or if this happens all the way down on the ground, you get fog. That brings us to Section 3, pollution and trapped air. So, how do we manage the pollution we put into this system? City planners actually rely heavily on a brilliant tool called a windrose. It looks a lot like a compass star, and it shows you exactly which direction the wind typically blows from in a specific area, and just how strong it is. Why does this matter? Well, if you're building a new factory with a giant smokestack, you look at the windrose to ensure you place that factory perfectly downwind from the city. This simple step ensures that toxic smoke is naturally blown away from neighborhoods rather than right into people's homes. But even with the best planning in the world, the atmosphere can still betray us through something called a temperature inversion. Usually, as we discussed, air gets colder as you go up. But during an inversion, this completely flips. First, on a clear night, the ground cools really fast, chilling the air right above it. Next, a warm layer of air forms aloft, sitting right above that cold surface air. The third step is where the trap snaps shut. That warm layer acts exactly like a tight lid on a boiling pot. The cold, polluted air from vehicle exhaust in factories literally cannot rise through that warm lid. It just gets stuck at ground level. This is exactly why cities located in valleys, like Los Angeles or Kathmandu, experience such severe, suffocating smog on winter mornings. Fortunately for us, the Earth has its own natural cleaning mechanisms. Meteorologists call this the scavenging process. Have you ever noticed how incredibly fresh and clean the air smells right after a heavy thunderstorm? That is wet scavenging at work. During what's called rainout, pollutants actually act as the microscopic seeds for the raindrops inside the clouds. And then there's washout, where falling rain essentially acts like a giant net, colliding with and capturing pollutants in the air below the cloud, washing them straight down to the ground. There is also dry scavenging, which is simply gravity slowly pulling pollutants down to settle on surfaces, like that fine layer of dust you always find on a parked car. Let's transition to Section 4, the changing climate. First things first, we really need to clearly define what we're talking about here. Weather and climate are not the same thing. Weather is short-term, we're talking minutes to days. It answers the question, do I need an umbrella today? Climate, on the other hand, is the long-term average of weather patterns over 30 years or more. It answers a much bigger question like, is this part of the world generally a tropical rainforest or a dry desert? When we talk about climate change, we are looking at a shift in that long-term baseline. The data outlines this shift through a process called the enhanced greenhouse effect. Let's go back to our earlier heat budget, but this time, imagine those greenhouse gases as a blanket. Naturally, this blanket keeps us warm and alive. It's a great thing. Then, human activities like burning fossil fuels and widespread deforestation release massive amounts of excess carbon dioxide, alongside methane, which is actually 25 times more powerful at trapping heat than CO2. Because of this, the atmospheric blanket becomes extra thick, and ultimately, this enhanced, thicker blanket traps too much of that outgoing heat, which steadily raises the average global temperature. The specific number measured by meteorologists for this global temperature rise since pre-industrial times is 1.1 degrees Celsius. Now, I know 1.1 degrees sounds like a pretty small number, right? But you have to view this in the context of a global planetary average. 1.1 degrees is a highly significant, deeply impactful amount of added thermal energy to our system. This specific added energy is actively driving the rapid melting of polar ice caps and Himalayan glaciers, which in turn causes the thermal expansion of our oceans and rising sea levels, directly threatening coastal cities worldwide. And that brings us to our final section, Section 5, Extreme Weather Events. When that unstable air we talked about earlier gets truly violent, you get extreme, hyper-localized events like tornadoes. A tornado forms when there is strong wind shear. That just means winds are blowing at different speeds and different directions at different heights in the sky. This shear creates a horizontal spinning tube of air right inside a thunderstorm. Then, massive, powerful updrafts of warm air grab that spinning tube and tilt it entirely vertical. When that violently rotating funnel of air finally touches the ground, you get absolute destruction, with wind speeds that can exceed an astonishing 300 kilometers per hour. On a much, much larger scale, we have hurricanes, also known as typhoons or cyclones, depending on what part of the world you're in. These are literally the largest, most powerful storms on Earth, and they require one very specific fuel source, ocean water that is warmer than 26.5 degrees Celsius. The anatomy of these massive storms is wild. Right in the very center is the eye, a deceptive, clear pocket of calm air and extremely low pressure. But immediately surrounding that eye is the eye wall, a tight ring of the most violent thunderstorms and the absolute strongest winds. And the real danger here isn't just the wind, it's the storm surge. We're talking massive walls of ocean water pushed miles inland. But because they are so heavily reliant on that warm water fuel, they weaken almost instantly the moment they move over land or cold water. Finally, let's zoom out and look at the biggest global weather switch of all, situated right in the Pacific Ocean, the El Niño Southern Oscillation. During an El Niño event, typical trade winds weaken and warm water flows east towards South America. This single oceanic shift acts as a massive global domino effect. It causes devastating floods in South America, severe droughts in Australia, and dangerously weak agricultural monsoons in Asia. Conversely, a La Niña event features a cooling of the central and eastern Pacific, which generally brings the exact opposite effects, like much stronger monsoons to South Asia. It perfectly illustrates just how deeply connected our global weather engine truly is. So there you have it. We've gone from the microscopic molecules of gas we breathe all the way up to massive global cyclones and shifting climates. Our atmosphere is a highly sensitive, interconnected cause and effect machine. And as we continue to measure changes in the system, it leaves us with a critical question to consider. As our atmospheric engine continues to shift and drive more of these extreme events, how will we adapt our cities, our agriculture, and our daily lives to this rapidly changing environment? Thank you for exploring the incredible mechanics of our sky with me on this explainer. Keep looking up and keep asking questions.